Hey guys, how's everything going? This is JSer. In this video, I'm going to take a look at 5455, minimum number of days to make a M bouquet. The problem is, I did this morning in the live contest, but I didn't make it. I tried to solve it with recursion. Well, of course, I got a TLE and I was stuck there. And after the contest, I see other people's solution, and realized that wow, it could be so simple, and I found very interesting. And so I'll make this video to try to explain it with my own words and to see if I can explain it to the possible interviewers. And so I'll try to explain my thoughts on the recursion, and I try to solve it and analyze the time complexity, and use the other people's solution with binary search. Okay, hope it helps. Okay, so we're given an integer array, bloom day, an integer m, and an integer k. So this bloom day means, okay, we need to make n bouquets. This is our target. And integer k means I need to use k adjacent flowers to make one bouquet. The garden consists of n flowers. The ith flower will bloom in the day bloom day I, and then can be used in exactly one bouquet. Okay, and then we need to return the minimum number of days I need to wait to be able to make n bouquets from the garden, and that it's impossible to make n bouquet. Return -1. So let's take a look at the examples. Suppose we have an array like this. It means the first flower will bloom on the first day, the second one will bloom on the 10th day, a third one will bloom on the third day, the fourth one on the 10th day, and the last one bloom on the second day. We need to make 3 bouquets, and we need only one adjacent flower to make bouquet. So the explanation is very straightforward. So after day 1 is something like this, right? Because the first flower bloomed, and after day 2, the last flower bloomed. So we can use these 2 flowers to make 2 bouquets. And day 3, this one blooms, so we can make 3 bouquets. Well, take a look at example 2. For this case, we need to make 3 bouquets, and we need 2 flowers to make 1 bouquet. So we need at least 6 flowers, right? And we only have 5 flowers. So no matter how long you wait, there will be only 5 flowers. It's impossible to make these bouquets. And the last third example, we got 7 and 1, 12. We need to make 2 bouquets and 3 flowers to make 1 bouquet. So we need 6. So if we wait long enough to wait for all flower blooming, we can make enough bouquets. And if we only wait 7 days, and you see we can only have these flowers and these flowers. So these 2 flowers cannot make a bouquet. So these can make at most the first one and the last one. Oh no, the one, right? So after 7th day, we can only make at most 1 bouquet. So we need to wait a 12th, right? 12th day, and to make to 1, 2, right? Or 1, 2 here, 1, 2 here, it doesn't matter. And this, yeah, this day, wow, it's a very big day. And we need 1 bouquet with 1, so yeah, with this. And this is the same. So the input is very big actually. The number will be 10 to the power of 5. The bloom day will be to the 10 to the power of 9. Yeah, how we solve it? Well, the first idea comes to my mind is recursion. Let's try to solve it, okay? The idea is simple. Suppose there is an optimal combinations of the flower, and we take a look at it if the first one, okay, we could take the last one is better, right? If the last one is in our array, if in our picked flowers, if it's in it, and if it's in it, we need to k, right? We need k flowers to make 1 bouquet. So the continuous k elements ending at this index will be used to make 1 bouquet. and the max number in this array, in this continuous subarray, will determine how long we have to wait, right? So, and if we remove these subarrays, we can reduce this into a sub problem, which will make n-1 bouquet with the rest possible flowers, right? If we don't use it, when we can just remove this flower and doing it to the rest. Well, so if we think that the minimum, so min I, which is minimum days at ending at I, right? So it actually equals to, there will be two possibilities when the I is used. So if that's the case, what we need to the min I minus k, right? If it's 1, then okay, minus k. Okay, the idea here is m, so it should be m minus 1, right? And the rest day, and we need to choose the bigger one, right? Yeah, so math max the days would be, how can I say, the math max bloom. Okay, I just say cost. Okay, min bloom how can I interpret this? This should bloom n I. Okay, so the bloom and I actually should be what? Should be math max boo day I. I'll just make it like this, right? N minus k. No, it should be +1 and I +1. Okay, I itself. Yeah, this is the blue man. And or, so this is one possibility. When it is used, we should actually have a minimum. If it is not used, it should be minimum I minus 1m, right? So this is our actually recursion function. We could use this to use this formula to create a recursion solution, or I think a dynamic programming. So in this approach, I'll first try to implement it and then analyze the time complexity. Okay, so I'll use the recursion plus memoization. Cool. So the recursion should be, I say, min days at, okay, ending at. So I'll use min days at. This is the index and the flowers. Okay, no, bouquet count, and the flower count doesn't change. So just ignore it. And so the entrance should be, the result would be, we get min days at ending at the bloom day. Okay, the bloom day is a little different. We use bloom end, right? Maximum the days. So rather than we compare all the bloom days, maybe we could get to generate like a cost array, which means we need to get the cost. If we choose the minimum day, minimum day, we need to wait ending at a specific index to make a 1 bouquet, right? Cool. I'll say I'll create a bloom n. Okay. So just bloom. Wait. This seems bloom weights. Looks good. So I'll traverse through the array. I think it should be k1. It should start 0. So k minus 1 is more than that bloom day I plus plus. So bloom I equals 2. It should be max, right? So it should be bloom day. We get the subarray. Oh. Slice I. This is I. Then this is if k is 1, it's itself. So I minus k plus 1 and I plus 1. And if we use right operator, and we can get the maximum, the bloom weight, the days maximum. Yeah, cool. So we now get the mean days at. Well, it's simple now. Oh, so the result will be, as we analyze here, it should be math minimum. The first one is the last one is used as a bouquet, right? So it should be math max. It's used. Cool. So if it's used, then itself will be bloom weights index, right? This is the days we have to wait. And what we do, we just get the minimum days I minus, which is index, minus k, which means the continuous k elements are used to generate this last bouquet, right? And the bouquet count should be minus 1, right? Yeah, this is one case. And another case is that it's not used as a bouquet. We could just do it recursively, call index minus 1 bouquet count. Cool, so this is the result. We actually could return this result. And it's done? No, it's not. We need to add some irregular and ending cases, right? The first one, as with analysis, we must at least wait enough flowers, right? So what we need, flowers, is bouquet count times the k, at least this flower. So if index is smaller than this, minus 1, if it equal, we could use them all as a bouquet. So if it is, we return, it's impossible, it's infinity, right? And also, if there's no bouquet we need it, so the last bouquet is generated, then if bouquet count is 0, then it means we don't need to wait, right? And 0. So this is it. And okay, the last call should be min days as minus 1. Could use push, right? Oh, I think I could use push. Yeah, bloom weights. And the bouquet count is m. We return if the result is infinity, then minus 1, not its result. Cool. So this is our general solution. Let's try it on the code. Oh yeah, it actually works. Let's try a more complicated example. It's like this: 4 2 4 2. Yeah, it's actually working. One thing, I forgot the memorization. Uh-oh, here's a problem. We output minus 1. This is wrong. Let's try to make it right. Let's log. I think I should not use push. The I would be better. Yeah. So yeah, this actually will work on our basic examples. But we forgot one thing. This recursion actually has a lot of duplicates calculations. When we're using recursion, like for this case, we're going back. Like for this 8, there were many possibilities to the left and many possibilities to the right. So for this 8, there will be multiple cases that it is called with the same bouquet count. So this actually we could cache that, right? So let's try to use memorization. We will add const cache equals new map. Of course, the key would be index and bouquet count. If it is already cached, we need to set the cache, right? Cool. So this is our memorization, and it should work. But of course it will get TLE as I did this morning. It's not only TLE, but actually memory is not enough. Keep up out of memory. So it's very important. Performance is very bad. Let's try to analyze why the performance is not good. Well, we use memorization, but if we take a look at our example, we will see that for every flower, generally, if k is 1, it means we are going to have for each flower, it might be used for a bouquet, and it might not be used as a bouquet. So there are two possibilities, right? So I haven't dig deep into the real right time complexity, but actually our solution will traverse to loop through all the possibilities. This actually generally it will become 2 to the power of n possibilities. Actually, suppose the n is the possible flowers count. Yeah, so time complexity is this, and our cache, well, we're still using every possible key. It's like suppose these n flowers, and the bouquet count is m, so it's will generate n k and m, right? Well, so this is our solution with even with memorization. We take a look at all the possibility generally. If k equal, this is when equals 1, the special case. Cool. So you see that it's not very good. It's exponential. It will not be accepted by LeetCode. So how would we improve this? Well, I didn't think of this. So the other people, they're very clever. So the key point to this problem is that we must realize that if we wait long enough, right, all the flowers will bloom. So the worst case is the maximum day, right? The worst, we just wait all the flowers to bloom so we can create enough bouquet we want. And the fastest it will be today, right? We don't wait, so we just create all the bouquets we want. So rather than the combination is the exploitational, we could just to search the day with a binary search, and yeah, so that's really clever, I think. Let's try to see what would happen if we use a binary search to search the day. It's like as I realized, I remember there is a problem called the first bad version. We commit a. You can search on LeetCode. There's a. I also have a video to explain that. So we need to find the first bad version in our commit log. This is actually the same, right? We need to get the first day we could make an bouquet. So it looks like similar. So I'll remove the code here. This is a solution with binary search. So the key point is we could wait long enough to create an bouquet. Yeah, the days are finite. Binary search. So first we get the max. We loop through all the bloom day, get the max day, so it's linear time. And now we could do binary search to check if we could. So these will be log n, right? 3. To check, we could how we check. We just like for going to day 3, we just loop through the bloom day and to see how many flowers are already bloomed, right? So this is what generate linear time. So in total, it's very clever. Comparing our exponential time complexity, we have improved it to what? N log n. Wow, that's a huge improvement, right? So yeah, let's try to do that. Cool. But first we get the max day. Okay, bloom. Okay, I just okay, I can just the end. Okay, the start equals 1 and constant n be math max bloom day. We now get the n. Cool, and then we just can start binary search. Wow. Start smaller than equal to n, and get the middle. If is possible, middle. If it is possible, then there might be some more possible sooner than this day. So what we do, and set to middle -1. If not, we move start to the next, right? The typical binary search. And finally, what we will do, we will return the start. Yeah, start will be actually the first possible. This is the first bad version, first valid version, I think. Well, let's filter out the invalid cases. So if n k is bigger than bloom day, then return -1. So the other if we have enough flowers, we always could have a valid result. So we return start. So now what we need is we only need to create this is valid function, right? Which is day. So for this day, what we do, we just count the flowers. Well, there's a problem is that we need adjacent. It's something like for bloomed, and bloom, something like this, right? So it's kind of like a buffer. So actually, we need to count the buffer and divided it with k to determine how many bouquets we want. This is the count of the flowers. Cool. Let's create buffer count. Buffer count equals 0, and then we'll loop through it for let day I of bloom day if day Well, if okay, if I no, this is the a day. This is bad. I would just say this is target. Let day of bloom day. If day is satisfied, means bloom, right? So we update the account. If not, we need to set it to 0. But before we set it to 0, we need to determine how. Okay, the count of bouquet. Count of bouquet 0. We need to add it to increment the bouquet count, right? So plus, so like this bunch of flowers, like 5 with the bouquets k, how many flowers? Well, we could divide it just right. Divided by k, right? Math, floor. This is buffer count. Divided by k. Okay, I rename it to like bloomed count. This is better. So this is the count we could get. So and then we would return is bigger than m. It means whether we can make m bouquet at the target day. Cool. So that's it. Let's try. Assignment to const. Oh shit. I'm sorry. Ooh. We got something wrong here. Ooh. Really? We get the wrong answer. There's something wrong. Let's review our code. Okay, we get the end. Start, middle. Possible. We update end. If not possible, we update start, and the last we return start. This is right. So it's possible we get target. We bloom count 0, count of bouquet 0. If this means the bloomed, and we update the bloom count. Cool. And then we made something. We made a flower that hasn't bloomed, so we set bloom count to 0 and update the count of bouquet equals bloom count equals divided by k. Wow. Wow, I think I didn't find something wrong. Oops. Let's count the log target. Count of bouquets. For this case, we first check 5. For 5, 1, 2, 3. Actually, we get 3. Why we get 2? Yeah, the ending. I forgot the ending, man. I forgot the ending case. I need to update it one more. Yeah, this looks not cool. Okay. I just think it's cool trading flowers. Cool. So looks good. Let's submit. Yeah, we accept this. So let's try to analyze the time complexity here. As we analyzed before already, its time will be much better, much better. This space. About space, we actually we don't use any extra space. Why it's so cool. It's constant. Wow. Yeah. So okay, so that's all. Hope it helps. Wow, this really, I learned a lot from this problem. That though the problem looks different, but if you take a closer look, it's similar to the first bad version. It's kind of binary search. Yeah, it's hard to think about that. And anyway, let's practice more. See you next time. Bye bye.